paying good money.
You gotta sap up as much electric as you can.
I'll get them on, no problem.
I'm going back and doing the ultimate stuff.
Some programs too.
I know. I have the first class, I have a big project and then two slightly smaller projects, and I also have a Java project. I'm working on all three at once.
All this semester?
No. I was thinking of taking off one semester.
Two, the only thing that takes a while is like the big project. Because he has like a big project that takes, that's like the only other reason
Or not?
Because that was the one we did, that was like your arm for there you go, challenge.
I don't want to hurt you and just
C++ is easy because you get, present like that, 200%.
I already that. I think it's
Okay. So what do you have left?
Java, high school, computer science,
Computer science is easy. I haven't taken assembly yet. That's supposed to be.
well, that's not the point. Java and assembly.
I think Java and computer science too.
There's better ways to do that. Which is pretty interesting.
I don't think I'm going to try it, but I was
It's just a way to separate the different, from assembly, calculus to
calculus too.
Yes, sir.
the model.
Nobody ever says I like calculus.
I didn't dislike it. I liked it. It was the hardest math class I've taken, but I still liked it. But then again, I'm weird.
Actually, it depends on the instructor who teaches you.
What's that?
Completely depends on the instructor who teaches you.
Well, that's true.
Yeah, because calculus 5, it could be really good, like, or else you could really hate it.
But yeah, it was, I had to spend hours, going just because the concept, it was there, but then applying it, well, I think I understand it, and then you try to apply it, and, well, maybe I don't quite understand it.
It's very
It's because it takes so many steps, and if you change one step midway, you're like, how do I solve this?
Is calculus 5 more difficult than calculus 3, right? Calculus 2 is difficult than calculus 3.
Oh yeah, much harder than 3.
Right? That's what everybody says.
Calculus 2 is the first math where it's not using, it's not introducing.
So what you can do
now, it's like actually using it. Like everything in calculus 2, I think is
and now, because like if it says just like for instance, prove to someone,
the way that they're actually
you don't have it so you just say, okay, well, I'm going to fact it.
so it's like,
so that's why you have to keep auto because yeah, because I mean, sometimes it's easier just to use the direct proof instead of the case in mind. Sometimes you can't use it.
This you do.
So when you can't, I've changed spaghetti. Okay guys, so what we're going to do today is we're going to finish up our proofs with the floor and ceiling. And then we're also going to take a look at indirect proof methods, okay? And then don't forget guys, by Monday, make sure you guys have assignment 5 for me. And if you guys have some questions, I'll be happy to answer whatever I can. Okay. So last time we went through the definition of what floor and ceiling were. This is our definition of floor. Okay, so remember guys, for any real number x, the definition that we're going to utilize is that x rests between two integer values, okay? Such that it could be equal to n, but at most it could be n minus 1 for the floor of that, or n plus 1, excuse me. And then for the ceiling function, okay, that there exists some real number that the ceiling of x is between these two integer values, it could be the maximum, okay, but it can't be the minimum value for this, okay? And we're going to utilize these definitions today to be able to do some proofs involving floor and ceiling, okay? So, last time I think we did our div mod, we did like our quotient remainder theorem, and that sort of stuff. So today we want to go ahead and actually implement this. So, the first proof we're going to look at is we're going to use a direct proof to verify that if for some reason I took the floor of x minus 5, where x is a real number, that's equal to the floor of x, and then minus 5 from that. Okay? So before we do anything with this, let's just make sure that this statement's valid. Okay? We don't want to go through and prove this if it doesn't even work. Okay? So, Andre, give me a real number.
5.
Give me a real number that's not an integer.
6.1.
Okay, 6.1. Thanks, Andre.
Okay.
So, floor of 6.1 minus 5 hopefully is equal to the floor of 6.1 minus 5. Now, this is going to be 1.1 inside the parenthesis. Guys, what's the floor of 1.1?
1.
Over here, the floor of 6.1 is 6 minus 5. So at least for a very basic trivial case, it looks like it works, right guys? So we don't necessarily have any reason to doubt it yet, okay? So does that make sense, guys? Always go through in real life, okay? Now in math life, you guys know I'm going to make it work no matter what, because I wouldn't just give you a problem that you could just do that easily and then just get 10 points for that. Sorry, okay? So let's go ahead and do our proof, okay? Let's start by defining some variables. We obviously need to define a real number, okay? But we're also, because we need to use the definition of floor, we're also going to define an integer n, okay? Just because we need the definition. So here's what we're going to do. So let's let x be an element of real, and let's let n be an element of the integers, okay? And then in our brackets, arbitrary, a particular, yay. Now, this is one of those types of problems where we don't have a definition for real numbers, we don't have a definition for integers. What's the only definition that we really have? The definition of floor, right? So let's just use the very definition of floor, okay? So, we know that there's some integer, okay? So, there exists some integer n, or there exists n, such that the floor of x is equal to n, right guys? We know that that has to exist, okay? We don't, I mean there's no doubt about that, okay? Like if I took the floor of 4.2, that's 4, it's an integer, okay? That's the very definition, the very nature of the floor function, okay? Now we can use the floor function, okay? So by definition of floor, this animal right here, couldn't we rewrite this just as this right here? That's the this guy right here. That's the very definition of the floor. So that's going to be n less than or equal to x less than n minus 1. Okay?
Plus 1.
Plus, I keep doing that. Why do I keep doing that, Art? I don't know.
Maybe you didn't have your beer.
I know, I really need some more beers. Just I didn't have enough at lunch. I didn't have any, unfortunately.
That's definitely not enough.
I know, that's right. The ceiling of beers, not the floor. Oh, that's funny, we're in a math class. Alright, now, I'm trying to show this true for the floor of x minus 5, right? So guys, think about a compound inequality, alright? Because I'm looking to prove this for x minus 5, couldn't I legally, and algebraically, couldn't I subtract 5 from all 3 of the parts from this? Okay, for those of you guys that have worked with, what is it, the interval of convergence, you know that this is a typical type of compound inequality you have to work with. Okay, so n minus 5 less than or equal to x minus 5, and that's going to be less than n plus 1 minus okay? And that's just by simple subtraction, okay? And everybody here agrees that's true. Like if you plugged in the numbers 2, 2.5, and 3, no matter what, if you subtracted 5 from all 3 of those, it would still be a true inequality, okay? So that's just by subtraction. Now, what can we say about this whole mess right here if I wanted to go back and reuse the definition of floor again? Okay, so let's just go ahead, go backwards from the definition of floor. Okay, so this is one of these where somebody kind of has to show you guys at least initially how this works. Okay, but does anybody think they might know what this whole animal could become if we kind of look at it like this? Anybody want to have a guess? Or? Well, this, if I had the floor of x equals n, and then I subtracted 5 from everything, right? Wouldn't this be the same thing as the floor of x minus 5 now? Okay? Because now, isn't this the exact same thing, but instead of x, we just substitute that with x minus 5, right?
Mm-hmm.
Like if I had a minus 2, I would just have an a minus 2 in the middle of that, okay? So it's basically we're subtracting 5 to make it fit the definition of floor. Okay. What is that equal to? Because the floor of x is equal to n up here. So what should this be equal to? Anybody think you might have a guess? N minus 5. Nice job. So basically, all we did was we just used the definition of floor to be able to subtract 5, and just to write it in that form. Okay, does that make sense to everybody, guys? It might be difficult to see, but we're just using the definition of floor to be able to work this. Okay? Now, I'm almost done, right? All I'm trying to show that this animal, x minus 5 floor, equals floor of x minus 5.
But you already showed that.
Oh, I did! What, and James, what do I know about the floor of x? What is that equal to?
N.
And couldn't we just substitute floor of x in for n? And we're done, right? Guys, check this out. N up here, we'll just pull some magic, is equal to the floor of x. So we get the floor of x minus 5 equals the floor of x 5 less than that. And that's just a substitution, right, guys?
That monster, when you put subtraction, just turns into the floor of x minus 5.
Right. This whole statement right here is the very definition of floor of x minus 5, not just floor of x.
We can do that because we set the floor of x to equal n.
Correct, right? Okay. And it's some integer, right? So, and that's why this is completely legal, okay? We're basically just subtracting or adding what's inside there to make it true. That's all we're doing, guys. It's not meant to be too difficult. Okay. Questions, guys? We'll finish it off in a second, but I want to make sure at least the algebra component's okay with this. Okay? Guys, we could just say, thus by above, the original statement is true. Okay, I mean, this is the definition of floor, so by above statement is true. Or valid, or whatever you want to say. I'll just say true. Guys, these are actually fairly simplistic proofs. I know for some of you guys it's like abstract as to where this is coming from, but basically we're just going ahead, using the definition, modifying the definition, and putting it back into the original form. Okay? So any questions, guys, before we try sealing proof? Okay? I think once you have one of these, most of them look the same. Okay? Like for instance, okay, the second example we have, okay, is that if I have any integer, and I should have defined m to be an integer, so let's do that first. Okay? So, for any integer m, the ceiling of x plus m is going to be equal to the ceiling of x, and then plus m. Okay? So, this time, instead of using the definition of floor, we're going to utilize the definition of ceiling. And guys, to use the definition of ceiling, you have to have a real number x and an integer n. Okay? So let's define those. Okay? So we start by saying, let's let x be an element of the real numbers. Let's let n be an element of the integers. Okay? And we do our arbitrary with particular stuff. Isn't it true, guys, that there must be some integer n that equals the ceiling of x, okay? I mean, if a ceiling function is greatest integer function, okay? So, there exists n such that n is equal to the ceiling of x. Okay, we know this. Okay. Otherwise, there would be no such thing as a ceiling function. Okay. So, guys, what do you think the next thing we should do with this is now that we've defined that there's some integer n?
By definition of
Let's use our definition of ceiling, right, guys? I mean, when we've defined ceiling, we have all the variables there. Let's just go ahead and use it, okay? So, our definition of ceiling, okay, we would say that n minus 1 is less than x, which is less than or equal to n. Okay, that's the definition of ceiling. Okay. So there's no algebra so far with this, guys. All we're just using is definitions that we're given. Okay, so this is nice thus far. I don't think it hurts anyone's feelings, and if it does, too bad. Does somebody have a suggestion as to perhaps how we can get to x plus n based on what we did before? Go ahead.
Plus m on everything.
Yeah, on the sides and in the middle. Let's just use that rule of addition of inequalities. Okay, so Greg, I like your idea. So n minus 1 plus m less than x plus m less than or equal to n plus m. Okay, completely legal. Okay.
That's just by addition, right?
Yeah, that's simply by addition. Okay, it's an inequality rule. Okay, and it's an inequality rule of addition. Okay, so we're just going to say by addition. Okay. So, just looking back at the previous proof, okay, or maybe you just know, okay, what would the next line look like if we were to try to convert that back into the definition, or using our definition of ceiling? Anybody think they might know?
Yep.
So, Greg, go ahead.
Ceiling of n plus, or x plus m equals n plus m.
So ceiling of x plus m
Would equal n plus
would equal n plus m. Okay? That's the very definition of what that we just said was. Okay. So all we're doing is we're just basically thinking of it like we're just getting the definition, we're adding m, okay, and we're just transforming it. Okay. For those of you guys that suffered through differential equations, Laplace transforms, you transform it into an algebraic, you solve it, and then you can solve it as a differential. Same sort of thing. We're just transforming it into, yeah, a lot easier said than done, right? Yeah, those are painful, by the way. So, sorry. All right. So this is our definition of ceiling again. And then, guys, just like the last proof, what's the last thing we might do with this? Substitute back in for n, right, guys? We know that n is the ceiling of x. Okay. So we get the ceiling of x plus m is equal to the ceiling of x plus m, and that's just by substitution. Okay. I'll get out of your guys' way so you can copy this down. Alright. Nice and easy, right, guys? It's not meant to be difficult. Okay. Just like we said before, by above the original statement is true. Okay. So by above this statement is true. Okay, so let me let you guys gander at that. And if you guys have some questions for me, I'd be happy to answer whatever I can. Okay? Go ahead, Greg.
So you're saying that ceiling of x plus m equals ceiling of x plus m,
Correct. For any integer n.
and it's
Right.
not, it's equals the ceiling of x plus m.
Correct. And if you want to, you can just start thinking of some numbers just to verify it for yourself, okay? It does work, I promise. At least for the last 12 years that I've taught it, it's worked. Maybe it changed, I don't know, but I'm just messing with you, it hasn't. Okay. Other questions, guys, I can answer about this? Okay. All right, let's do one more, but this time there's a condition that's imposed upon our last proof. Okay, so for the last one we have here, for all even integers, n, the ceiling of n squared divided by 4 is equal to n squared plus 3 over 4. Okay, so we can see that this is, what's that? Oh, I'm sorry, did I say even? Yeah, that's probably not a good idea then, because then it wouldn't be true, and then we could just say we're done with it. So, sorry, no, I would just impose about 10 more minutes of pain. All right. You might just want to pick like an odd integer, just to see if it works. Okay, let's just pick something basic. Let's pick 3, might as well. Okay, so again, just to verify that this works. So 3 squared over 4 ceiling is equal to 3 squared plus 3 divided by 4. Let's see if this works. Okay, this is 9 over 4. 9 over 4 is 2.25. Ceiling of that is 3, right, guys? Over here, 3 plus 3, or I'm sorry, 9 plus 3 is 12. 12 over 4 is going to work out to be 3, right, guys? So it looks like it works. Just for a trivial case, okay, we don't have to plug in something like 1001, although it would probably work for 1001 if we wanted to. So let's go ahead and prove this. Now with this one, we don't need the definition of floor and ceiling, right? Because don't we already have something that we can use a definition for? The odd number. Okay, so let's just use that and see if it works. Okay, so the only variable we need is just integer n, and we're going to define that to be z odd, right, guys? Because we're told that for all integers, or for all odd integers, n. Okay, so let n be an element of the integers odd. Okay, arbitrary of particular. And you guys know the definition of odd. That's going to be equal to 2k plus 1. Might as well use it. Okay, so by definition of odd, n is equal to 2k plus 1. Okay. Most of you guys did a really nice job with this. A couple of you guys on the assignment that I just graded forgot to define the variable. Okay. If you forgot to define variables in this assignment, I just circled it and say don't do this again. I just defined it for you. But as we go along and we're getting more mature with our proof process, we want to make sure anytime we instantiate a new variable that we define the domain of that variable. Okay? All right. So does anyone think they might have a suggestion at this point once we've gone through and defined n to be odd?
Plugging in,
And
substitution.
substitute, right? Let's just substitute into both sides of what we're given. Okay, sounds good to me. We usually do with even and odd. So by substitution, this becomes the ceiling of 2k plus 1 square divided by 4. And we're hoping that that equals the quantity of 2k plus 1 squared plus 3 divided by 4. Okay, so that's just straight substitution. We're not using the definition of floor and ceiling for this one because we're already given a predicate condition that's saying it's already going to be odd. Okay, so we don't have to worry about that. Okay. What seems like the most obvious thing to do at this point?
Expand it.
Expand it out, multiply it out, right guys? I mean, every time we've had something squared, we've had to expand it. So let's do that, okay? If we were to FOIL this out, 4k squared, please don't say 4k squared plus 1, plus, not 2, but
4K.
4k, good. And then plus 1, right guys? Okay. And by the way, if you don't know how to do that, what do? You just write it off to the side, you FOIL it out, right guys? So what you guys can do is just do 2k plus 1, 2k plus 1. That becomes 4k squared plus 2k plus 2k plus 1. In other words, 4k squared plus 4k plus 1. Okay? So, I'm assuming most of you guys are good with that. Okay? But if not, just go through, do the algebra, knock it out that way. Okay? Won't hurt my feelings either way. As long as you get it right, you don't cheat. Alright. On the right-hand side, same exact thing, except we have a plus 3 in the numerator. Okay? So, 4k squared plus 4k plus 1 plus 3 give 4. So, that's just by FOIL, multiply, expansion, polynomial rules. We'll just say multiply. Okay. So, I'm guessing everybody knows what to do on the right-hand side of this, okay? 1 plus 3, okay? That's easy. What about the left-hand side? Does anybody think they might know a way that we might be able to prove this thing, Michelle?
You could just factor out the 4 from the first two terms, and then you could, then you'll have 1/4 in your credit.
Oh, okay, so maybe just break it up into maybe 3 fractions, or factor it out, whichever way you want to do it. I like your way too. I was going to do this, and I don't care which way you do it. I like your way fine, because you can cancel it out. I was going to do this, have it as 4k squared over 4, plus 4k over 4 plus 1/4, and I think we both arrive at doing the same thing. We get that 1/4, because I think you see that you need that 1/4 to make this work. Okay, nice. Okay, and that's legal, right, guys? We're dividing by a monomial. You can break it up into 3 separate components. Could we do the same thing on the right side? Sure. Okay, we can break that up into 4k squared over 4 plus 4k over 4. And then you guys know 1 plus 3 is 4, so we'll just say 4 over 4. Okay? That's just division, okay? Everybody sees that. That's something that we've done probably more times than we ever care to count in our lives. Okay, so just some division there. What's beating ourselves upside the head for us to do now? Yeah, simplify it down. So let's simplify it. I mean, that's why we broke it up. Good. So inside of the ceiling, this becomes k squared plus k plus a 4th, right? On the right-hand side, k squared plus k plus 1. Okay, that's nice and easy. Okay, again, that's division if you want to call it again. So 2 division steps. And Michelle, was that what you were thinking, like, to get down to? And whichever way, like, you just factored out the first 2 and it still worked out nicely. Good stuff. Okay. So, does anybody have a suggestion at this point as to what's going to go on with this? So, Brian, what do you think?
Isn't doing that the same thing as taking the ceiling of each individual term?
Unfortunately not. Okay, so it's not a linear process. Okay, like for example, okay, let me just give you an example of that one that wouldn't work. Like if I had this ceiling of 1.9 plus 1.6 equals ceiling of 1.9 plus ceiling of 1.6. Okay, actually that would work. I lied. So there we go. But wouldn't this become 2.7? Ceiling would be 3. Ceiling of this is 2, ceiling of this is true. So is 2, and 3 obviously doesn't equal 4. So unfortunately, it's not a linear process, okay, meaning you can't distribute that. So good try, okay, but unfortunately not. Any other suggestions, guys? So, Michelle, go ahead.
K is integer, so that isn't explicable.
Okay, so you have an integer plus an integer plus a 4th, right? So let's say k was like 1. 1 plus 1 plus a 4th just goes up to what, guys? 3. It just goes up to the next integer, right? You're on the right track, okay? I think what you were thinking was right for this problem because they're integer values, okay? So, guys, the ceiling of k squared, because it's an integer, isn't it still k squared?
Mm-hmm.
The ceiling of this k is an integer, so the ceiling is going to be k. But the ceiling of 1/4 is going to become what, guys? 1.
Yeah.
So doesn't this just, oh my god, I almost forgot it with this. How many of you guys have seen one of the teachers write on your pad? And they're like, oh my
Yeah, I
god.
was looking forward to seeing it for the first time, though.
Wow. So you're going to let me do that? Wow. That's why he's cool, bro. I thought we were cool.
I'll go let them know too.
Shut up. Alright. But guys, that becomes k squared plus k plus 1. That's the very definition of what the floor function does, right? Integer plus any decimal just goes up to the next integer. The right-hand side is static. There's no more operands to perform there. K squared plus k plus 1. We done, right, guys? That's the definition of ceiling, by the way. And remember, k has to be an integer, right? But didn't we define k to be an integer at some point? We did right there. Okay, so we're straight. Okay, we didn't do anything illegal. Not yet. Okay. So, this is our definition of floor. Oh, ceiling. Duh. Yeah, that'd be bad to use the definition of floor when it's clearly a ceiling proof. Okay?
Well, you were thinking about drinking.
Yeah, that's true. That's a good excuse. I like you getting that. Working. Okay. So,
Can I ask you one question?
sure, go ahead.
If it was a floor, then it would have become 0, right? K squared.
That's
plus
correct. Okay, that's actually important because there might be one on the homework like that. Okay, let's say, and let me write that on the board. Let's say you had this: the floor of k squared plus k plus a quarter. Okay, or what were you saying that becomes?
0.
Okay, well, not the whole thing, but k
K
squared.
squared plus k plus 0.
Right. Okay, because it's a floor, and the floor of the quarter is going to be 0. Now that's only if k is an integer, right, guys? So, if k is not an integer, if k is real or rational, all bets are off. You can't say anything about that. Okay. I think on your homework that's going to be helpful. Okay. So make sure you guys use that. I don't know which question it is, but when we're done, if you guys remind me to look at the homework, I can give you guys some hints. You have it, Donnie? Do you mind looking it up real quick and seeing? There should be one that says either even or odd or something like that. Number 4, is it? Or
Number 8.
oh, it's number 8. Take a look.
Yeah, I see it, yeah.
What does it say?
For all x, if the e thingy is z odd,
Okay.
n squared over 2 floor equals n squared minus 1 over 2.
Okay. And so what you guys are going to do is you're going to use, it's not going to look like this, okay, but you're going to use this principle to be able to verify that, okay? So basically, guys, just make sure you remember that this does work for this sort of thing. You'll eventually get, I think it'll end up being like 4k squared plus 4k plus 1 over 2, like that. And then when you break it up, you get the floor of a half. Okay, so, and if you guys, of course, if you guys need help, you just come to my office. I'll be happy to help out. Okay. All right. So, by the way, that was really important. So, did you say that on purpose because you started working on it?
No, I was thinking about it.
Okay, that's a good thing to think about. So, good stuff. Yeah. So, make sure you guys use this for number 8. It'll be a lot more helpful than just trying to bully it and do something that you're not supposed to. Okay. Other questions, guys? Okay. So, I think we just have to write that last line on here and we're done. So. By above, statement is true. Okay. Alright, so we're done with direct proof, at least for now. Okay? Now we're going to start looking at a secondary methodology of proof, which is even more powerful, something called indirect proof. Okay? And there's actually 2 main methods that we're going to use for indirect proof. Okay? So, one of them's really easy, and then one of them's more difficult. Okay? The more difficult type is called method of contradiction. Okay? So, guys, remember, contradiction, okay, or what we're going to say with contradiction is, we're going to write the negation. Okay? Sometimes we can't prove something is true, but we can prove that its negation is false. Okay? Because remember, guys, a statement is either true or false, right? It's one of the two. Okay? Like for instance, if I said, Donnie, how much money is in my wallet right now? Huh?
None.
None? Okay. So I come out, oh man, I'm balling today. I got $20. Yeah, man, I'm gonna just put this right in my nose later. But no, you're wrong, and so you were incorrect, right? It's either you're wrong or right. Okay. So, and that's what we're going to do, guys. Sometimes you can't prove that something's true, but you can prove the negation is false. And remember, it's either true or false. So what you're going to do is you're going to write the negation. You're going to try to prove the negation until you find a contradiction, which is why it's called contradiction. If the negation's false, then the original statement must be true, because it's either true or false, okay? So does that make sense to everybody as to why this works? Okay, we'll go through some examples, obviously, and I'll show you the process. The easier of the two methods, but not as powerful, is contraposition. Okay? Guys, what do we know about an original statement and its contrapositive?
Negative Q, negative P.
Right, so if you have P implies Q, the contrapositive is not Q implies not P, right?
Mm-hmm.
Didn't we say, correct me if I'm wrong, but a long time ago, didn't we say that the original statement and the contrapositive are logically equivalent?
Equivalent, yeah.
So sometimes we can't prove the original statement, but couldn't we maybe prove the contrapositive? If the contrapositive is true, the original must be true because they're logically equivalent. Okay? So that's what we're going to do by contraposition.
And contradiction is true with the inverse then?
The negation, not inverse. Okay,
Inverse.
so inverse and negation are two different things.
Okay.
Okay, because it's not necessarily conditional. Okay, so with contradiction, we need to prove the negation is false. That's what we're going to get at. Okay, so contraposition, write the contrapositive, prove the contrapositive. If contrapositive is true, original is true. Okay, so this guy is very powerful. Okay, I've seen contradiction used many times, even in like middle level mathematics. Okay, so probably at some point, okay, you're probably going to have to use contradiction somewhere. Okay, whether it be math, computer science, engineering, something like that. Okay, so you're going to use it. All right, let's do a really easy example. Okay, I want to prove that there is no least integer. Okay, now you guys know this is true, right? I mean, if I wanted to find a least integer, I couldn't because I could just keep subtracting things from it, right, guys? So here's our proof. Okay. What I want to do is I want to start by writing the negation of this statement. Okay? Guys, what is the negation of there is no least integer? There is a least integer, right guys? So let's assume, here's the way that it usually starts. Let's say, suppose not, suppose there exists a least integer. Now, we're not saying it's true, we're saying suppose that it were, because we're going to try to prove this false. Well guys, if there's a least integer, doesn't it hold some sort of value or hold a variable? Let's call it m for some reason, okay? You can call it p, q, whatever you want, okay? So, let's define the least integer as m, where m is an element of the integers. Because if it exists, it can instantiate itself a singular value. Let's say m. And well, I won't write the arbitrary in particular. Done with that. Okay. Now, how can we show that this is false? So, go ahead, Michelle.
M minus 1.
Yeah, there has to be some number, n maybe, such that n equals n minus 1, right? So, let's let n be an element of the integers now, such that n equals m minus 1. Okay? So what does that mean about the relationship between n and m?
n is less than m.
N is less than m, right? So thus, n has to be less than m. Thus, n less than m. Which means what?
So it's a,
That means n, it means that n cannot be the least integer, right? It's a contradiction. It's so obvious, right? I mean, everybody looks at that and they're like, well, if n was the least integer, but now all of a sudden n is, couldn't I just keep subtracting 1 forever if I really wanted to? Like I could find p to be n minus 1 and q to be p minus 1, whatever I wanted, okay? So this is a contradiction. You don't have to do the dot, dot, dot if you want one to. So this is a contradiction. which means that there is no least integer, right guys? It means that the negation is false, which means that we cannot suppose there's a least integer. So this is a contradiction. The negation is false. And because the negation is false, what does that absolutely mean? The original statement is true, right guys? It's one or the other, it can't be both. Okay? So the negation is false, and thus the original is true. Nice.
You're gonna have a lot of these where we have to write them out.
Well, this is just like an introductory one, so, but yeah, as you found out, I know they're a pain in the ass to write out, but yeah, you'll probably have to write a few of these out, okay? So, not a lot of them. So that's the original.
There's a lot of grammar, isn't it?
Yeah, you don't get graded on grammar or anything like that. So if you say it ain't true, or that dare variable, or something like that, that's fine with me, that doesn't hurt my feelings, okay? Or you want to start using cowboy talk or something like that, or if you want to draw 10-gallon hats, never hurts. All right. So, any questions about this, guys? That's the basic process for this, okay? And I know it doesn't seem like it's very powerful, but it actually is a very powerful process of proof. Okay. All right, let's look at something that's a little bit more mathematical, okay? So for this time, what I want to do is I want to prove that for any integer n, okay, that 3, and what do you guys suppose that this symbol right here means?
Divides.
Does not divide, right? Because it has the line width through it. What'd you say, James?
A black hole.
A black hole, okay. So 3 black holes, 3n plus 2, okay? So whenever you guys see this statement, let's just assume that that means does not divide. Okay. All right. So I was just curious what the next one was. All right. So first thing we need to do, we need to write the negation of this, okay? Guys, what's the negation of 3 does not divide 3n plus 2?
3 divides.
3 does divide 3n plus 2. Duh. Okay, so if this is on a test and you write the negation, you at least get 1 point for this. Okay, so we start out again. We just say suppose not. Suppose 3 divides 3n plus 2. Okay. I'm down with that. Guys, if 3 divides 3n plus 2, what definition can we use? Rhymes with divisibility. Divisibility, right guys? Yeah, divisibility. It's not a word, but I was just trying to prompt it. Okay. So, by definition of divisibility.
Don't you have to write that by such that 3 is equal to 3 times 1 or something like that?
Well, no, we're not going to do that. Okay, I'll show you what we're going to do in a second. So, by definition of divisibility, what can we say about 3n plus 2 by our definition of divisibility? Well, it's divisible by 3, right guys?
Mm-hmm.
So it has to be equal to
3 times some factor.
3 times some integer, right?
Yes.
Maybe p. So this has to be equal to 3p, where p is an integer. Okay. Does that make sense to everybody, guys? Like, we've used the definition of divisibility before. That doesn't hurt anybody's feelings, right? Now that you see it. We need to come up with some sort of contradiction with this. And this one's a little bit sneakier than you would think. Okay? So, let's just throw out some ideas, okay? Does anybody think they might know an idea as to perhaps how to arrive at some contradiction? We don't care what contradiction we arrive at.
So should we do the algebra first? Or?
Such as what, Art?
Subtract 3p on the left and take 3 as common equals to 0.
On the right track. So let me do that. Let me take the 3p from both sides. Okay, so 3n minus 3p. Okay. So just by subtraction. And then what else do you guys think we might want to do?
Negative 2.
So maybe move the 2 to the other side. So maybe just get all the variables to one side. Okay, would that hurt anybody's feelings if we did that? Now we might not know why, we're just doing it, but at least we're trying something. So this is just by some basic algebra, subtraction. Okay, so that's by subtraction. by subtraction. Okay. And then,
Factor 3.
yeah, factor 3 out. Couldn't hurt, right? I mean, they both have a factor of 3. It seems like it's the only possible place we could go. Okay, so let's factor out a 3. N minus P equals minus 2. That's just by GCF if you'd like. And then
Divide by 3.
maybe divide both sides by 3. Okay, couldn't hurt. So N minus P equals negative 2/3. Okay, I mean, I'm liking this. This is cool. I don't know if it's right, but it's cool. So it's by division. It's right by that. One more step that we know how to do.
No, because it's become irrational, because closure, anti-closure.
So N minus P is a new variable, right guys?
Yeah.
Because they're both integers. We can use closure. Okay?
Closure.
Let's just call it M. It doesn't matter. So we get M is equal to negative 2/3 by closure.
And m is an integer.
Oh, M's an integer. That might be a little bit important, right? In fact, if we don't write that, the whole proof sucks. I mean, it might suck to you guys regardless, but
There you
all
go.
right. So, all this algebra is great, and all the steps that we've done are absolutely correct. Are we done? Have we hit a contradiction?
Yes.
And if so, what is the contradiction?
It's a rational number.
Yeah, negative 2/3 is not an integer, right?
Uh-huh.
But we're saying it's an integer, okay? So how does that work? That doesn't work. We can't have something that we claim to be an integer equal to a rational, okay? It's just like if that's our contradiction, right? So this is the methodology. We go through, we try to prove, and we try and try and try until we run into some contradiction, okay? So that's the contradiction that we arrive at, okay? So what we're going to say is that thus m equals minus 2/3 and m is an element of the integers. Okay. That is clearly a contradiction. Okay? Nobody in this class would believe that negative 2/3 is an integer. Okay? So we say this is a contradiction. So this is a contradiction. And because it's a contradiction, what can we finally say?
Original statement is true.
That the original is true because the negation is false. Nicely done, gentlemen. Okay, so this is a contradiction. The negation is false. And the original must be true. Or we could just say, and the original is true. Alright. Yeah, some of these are sneaky, okay? Like with even and odds, you just go through and do it. With perfect squares, divisibility, rationals, you just go through and do it. You don't have to be slick about it, okay? I think of like this like Calc 1 stuff, okay? There's a rule for every derivative, right guys? In Calc 2, you have to be slick about stuff, right? So this is what I equate to like Calc 2 stuff. Go ahead, Jay.
You can just find a number that contradicts it, could you just use that as part of your proof?
Well, that's only one number though, right? We're trying to prove it true for any possible number, right? So unfortunately, that would be 1 out of an infinite number of values. And how much credit could I give you for 1 out of infinity? Yeah. No.
Well, if you're saying any number fits this, if you find one that doesn't, then you know any number doesn't.
It says for all z, 3 does not divide it, okay? So we just have to show it true for any single value. So it's impossible to exhaust, right? Because the only way to prove something this true is to use exhaustion. And unfortunately, you wouldn't want to exhaust this,
Oh,
right?
you're talking about
Right.
It's true.
Right. No. So remember, because if you just prove that, that means you've only shown the negation true for one value. We have to show it true for all values. Okay? So, not a bad guess. Okay? I like the efficiency method that you were thinking of. So, I don't want to say lazy, but it's efficient.
If you write the negation and you show the negation is false for one value, is that good? Because you're showing the negation is false in one.
but we have to show it for all values, right? Because we need to show the original true.
Right, but you're stating the negation is true for all values. If you show it's false for one value, then you're showing that the negation itself is false. So
Just for that one instance, though. So, and you'd have to show the negation false for every single instance.
If you're, well,
okay.
I understand what you're saying, but at the same time, if you're just given the negation and you're saying prove the negation true or false, you can prove it false by showing one value that it's not true. Do you see what I mean?
I see, because you're thinking of like, you know, the when we had the finite domain, okay? So to be...
Well, I mean, if you have an infinite domain,
oh no, it's true if it's a for all statement, okay? Right. But we need to make sure that we're showing it for maybe there exists or something like that, so...
Oh, I get that this shows it false for all.
Right.
I get that, but if it's stating that it's true for all and you're showing, well, there's one instance that it's not false, well, then it can't be true for all, so you just proved that it's not true for all, so it's false.
I think you've only shown it true for that one instance. So
you showed it false for that one instance.
Well, okay. So what we're saying is, let's say like n is equal to 2.
Oh, you're saying because it was a negation and you're showing the negation false for one instance. It's only showing its original true for that one instance.
Right. So I was getting to that. So let me just go ahead and write it out what I was saying just to make sure. And what you're saying is valid. Like if you can find a counter example, okay,
right.
Then
that counter example is only proving the negation false.
Because n would have to be congruent to the original. Okay, so I mean, if n equals 2, okay, I mean that clearly doesn't work. 3 does not divide 3n or 3 times 2 plus 2, right? So that's true for that value. But if you guys were to substitute that, that's false, right? So this is false, but this is true for that singular instance, okay? So unfortunately, you can't just find one of them because of that. Does that make more sense now? Okay, it's valid. What you were saying is on the right track.
It's valid if you're only given the negation.
Right.
You're saying prove that true or false.
Right. Unfortunately, though. Not fortunately. Okay. Go ahead.
Okay. So just to make sure, so.
Do we go back?
Sure.
Okay.
That when, we'll just say that if you have a normal proof, like just saying if it's true or not, and then you have a contrapositive, one has to be true and one has to be false.
For contradiction, right. Not contraposition. So I think you might have accidentally said contraposition. But for contradiction, only one is true and only one is false. They both can't be true and they both can't be false. One must be true and one must be false.
So will there ever be a case where one of them is true and the other one is true?
No, sir. Cannot be.
So that would never happen.
Correct. It is impossible logically. Okay. And in fact, like go back to this, right? The negation of that. The original statement is either true or false. And that's the definition of a statement. So the very first definition we ever put up in class is a statement is a sentence that's either true or false, but not both. So it's either going to be false or true, right? So it has to be that. So it cannot both be true, it cannot both be false. It has to be one or the other. Does that make sense now as to why that is? Okay, yeah, that's like fundamental to the beginning of the class. I'm glad you brought that up. Okay, other questions, guys? Okay, let's take a look at this last animal here. Okay, and I think this is one of the most powerful methodologies of indirect proof is being able to work with irrational numbers. Because we haven't worked with irrational. We've worked with integer, we've worked with rational, nothing with irrational yet, because there's no definition for irrational. All right, so for all rational numbers x, if there's an irrational number y, then a rational times an irrational is irrational. Okay, let's just think to see if this is true or false. Okay, so somebody give me a rational number and an irrational number. Just give me like two numbers.
2 pi.
2 times pi, right? So 2 is a rational number, pi is an irrational number. So this is q, this is I. And guys, we know that 2 pi is irrational, right? If I said something like maybe opposite of 5e, okay? you guys know that that is irrational, right guys? So it seems like the product of a rational and an irrational is irrational. So it looks like the original statement's true. Let's prove it.
Can I ask you a question? Like, why is pi considered irrational? Because pi is considered the circumference over the
It's
radius.
the ratio of the circumference to the diameter,
So-
or of the circumference to the radius.
Radius. Then why isn't that the ratio? That's the ratios. Then why is it still considered irrational?
It never terminates nor repeats. It's just impossible to figure out the exact number of that. Okay.
No, but ratio is considered rational number, right? Ratio, any number that has a ratio.
Well, no, you're defining. You're thinking of ratio versus rational. Okay.
Okay.
Like for instance, that's a ratio, right? That's not rational.
Oh.
So there's a difference between ratio and rational. They're very close, but they're not the same thing. Okay, does that make sense, Art?
Yeah.
Okay.
Yeah.
All right. The discussion for pi is a completely different class. So, anyway. All right, let's knock this out. All right, let's define our two variables x and y. Okay, so let's suppose not, first of all. Okay. What do you guys think the negation of this would be?
So that is, there exists x, basically there exists x in the domain Q such that y, what's that, the same thing, domain
Same
irrational.
thing.
So not x, y is not irrational.
Is not irrational. Okay?
Yeah.
So remember guys, there exists some x, or we could just say that the negation of this, suppose not. Let's say suppose there exists x in Q, y in I, such that xy is in what domain? Is not irrational or
Rational.
is rational, right guys? Because that's what not irrational means. So such that xy is an element of the rationals. I'm going to put this in brackets. So Q is the same as not I. Okay, that makes sense. I mean, if it's not irrational, it must be rational. Okay. All right. So that's somewhat helpful. Okay. What can we say then? I mean, are there any definitions that we might be able to utilize?
Yeah, then x, y equals to a over b, c
Okay.
over d, like that.
Yeah, and couldn't we also say that x is rational? So couldn't we say, by definition of rational, we could say two things. We could say that x is equal to a over b, right guys? And we could also say that what? xy is equal to c over d, right? Because both of those structures are indeed rational, right guys?
We didn't define y to be
What's that?
Don't you need to define y?
No, y is irrational. Did we define y to be irrational?
Oh, okay.
We don't have a definition for irrational. Does that make sense, Art?
Got it,
Okay.
yeah.
Can't define it if it doesn't, or we can't use a definition if it doesn't have one. Okay. And of course, we have to say what about a, b, c, and d? They're integers. C and d, or b and d are non-zero. Okay. So we're going to say a, b, c, d are integers, and b, comma d non-zero. Okay. So I'm feeling that so far. And then...
So we need to do the multiplication and see.
But what multiplication, sir?
Oh no, sorry, we need to substitute.
Substitution, right?
Yeah.
Because guys, don't we already know what x is?
Yeah.
Couldn't we substitute back in for x? So we could just plug this a over b back in for x. I don't think anyone doubts that, right guys? So by substitution, we can say that xy equals c over d. Let me erase that. It's fine. Oh, that's helping a lot. Done. is going to be the same thing as what, guys?
CD equals to C over D times A over B.
Not CD, but you're
C-
close.
C over D, right? X, Y. You have to substitute the value of X is A over B, right?
A over B, Y. Okay, so A
A
divided
over.
by B times Y is equal to C over D, right? Does that make sense to everybody, guys? We just plugged in for X. Okay, maybe I just didn't say the question correctly. Okay. So what? How does that help us? Or maybe it doesn't help us. So, anybody have a suggestion to perhaps how we can encounter a contradiction?
We could solve for Y.
We could solve for Y, right? I mean, you could solve for A, you could solve for B, but I like solving for Y. I really like your idea. Michelle, how did you solve for Y? Or you just wanted me to do that part because that was
Well,
easy?
you can just multiply both sides by B over A.
Yeah, multiply by the reciprocal. Very nice. Should work in the learning center. I'm glad some people got that. That was pretty fun. I'm funny for that.
You're medium, Chris.
Yeah, I know. Okay. Guys, everybody agrees with that, right? You just multiply both sides by the reciprocal to be able to clear out a fraction. Okay? So Y equals CB, or C over D times B over A. Okay, that's just by multiplication. Nobody doubts that. Okay, so what? How does that help us? Maybe it doesn't, I don't know. So,
It shows that, well, Y would have to be a rational number technically.
because what do you know about C times B, John?
It has to be rational.
It has to be an integer. Right, you knew what it was. Good. Guys, don't we know that C times B is some integer value by closure, right? Let's call it P. How's that sound? Why not? So, let me actually make this a little higher so we can see what's up. Okay. So this means that Y is equal to P over Q, right? Just by closure. So P is an integer, Q is an integer, and that's by closure.
And Q is not equal
Yeah, Q is non-zero. Might as well throw it in there. It's not essential nor detrimental to the proof, but you are correct. All right. John, what were you getting at when you were saying that? You're absolutely right.
PQ has to be rational, but Y is supposed to be irrational.
That's a contradiction. Very nice, sir. Guys, didn't we at the very beginning of the proof define Y to be irrational? But isn't P over Q the very definition of rationality?
Yes.
Gone. No good. Contradiction. Okay? That's our contradiction at that point. Okay? So thus, Y is rational by definition of rational. Okay. But Y is an element of the irrationals. Okay. That's like saying a number is both even and odd at the same time. There is no number that's both even and odd at the same time. Okay? It's either got to be even or odd. It's either got to be rational or irrational. Can't be both. Okay? Thus, negation's false, original's true. We got it. Okay? So thus, our negation is false, and the original is true. And of course, whatever you put in brackets doesn't count. Blue jays suck. Alright. If you guys want to put that as a comment in there, that's fine.
So is there a negation of blue jays suck?
Yeah, blue jays do not suck. But obviously, remember, with any statement, only one's true and the other one's false. So obviously, it's true that the blue jays suck.
Will we get extra credit if you put that?
I'll tell you what, if you don't put it, I might take all points. Fine. No, I'm just kidding. They don't suck. They're actually pretty good. Okay. Guys, questions I can answer about contradiction. Okay. So the ones I showed you, these are the main methods I'm going to ask you guys to do. I'm not going to throw anything tricky in there, but there are literally thousands of contradictions that you could encounter. I just showed you guys some elementary types. Okay? Much easier is contraposition. Okay, so let's just go ahead and do maybe
So
a
contradiction has nothing to do with converse, right?
No, sir. No.
Okay. That's what I was making the mistake.
Right, converse is completely different.
Okay.
Okay, let's say for some reason you have an odd integer, and it's a square. It's a perfect square and it's odd. That means that its square root must also be odd. Okay? Now, remember, this is only true for perfect squares. We want to prove this for any sort of perfect square that's odd. Its root must also be odd. So, somebody tell me a perfect square that's odd, please. A perfect square.
169.
169, 1, that's fine. Okay, so 169, that's an even one, bro. Come on. I got it right. Okay, but so this would be n squared, and then this guy is n, right? And obviously that's the odd. And you guys could do the same thing with 1 as well, okay? But you could actually prove the same thing for even as well. The square root of a perfect square that's even is also even as well, okay? So, guys, it looks like it's true, right? I always like to just show it's true, just so you guys believe me before we do it for all. All right, now, we are not going to do this by contradiction, we are going to do this by contraposition. So the first thing we need to do is write the contrapositive, right? So, if I was to ask you guys, what is the contrapositive of this statement? Okay, and I'm going to put this in brackets. Okay, so this is the contrapositive. For all n in Z.
If n is not a member of Z odd, then n square is not a member of Z odd.
Okay, so.
You can just say L is even.
Ah, okay, there we go. So, if n is not a member of Z odd, then n squared is not a member of Z odd. Okay? Remember what contraposition says? Contraposition says that you flip the antecedent predicate and you take the negation. Or, as somebody else was just saying, what's another way that we could write this? If n is even, then n squared is even. Nice, Greg. All right. So another way to write this is to say if n is in Z even, because it's either even or odd, then n squared is in Z. Does that make sense, guys? All we did was we just flipped it around and we took the negation of it. Guys, isn't this a proof that we could have done the very first time we looked at proofs with direct proofs? Okay, this is about as easy as it gets. Okay? So, let's let n be an element of Z even, because we're trying to prove the contrapositive valid. And we can all easily do this, I feel. Okay? So, let's let n be an element of Z even. Okay? Because all we're trying to do is we're just trying to prove the contrapositive to be valid. Okay? Well, guys, if we know that n is in Z even, what does that mean? N equals 2k, where k is an integer. Nice, great. So, by definition of even, n is equal to 2k, k is an element of the integers. Okay, I'm feeling that. Once we use the definition of even, okay, what's the next thing we should probably do? Substitute, right? Nice. Guys, every time we have even and odds, it's almost like substitution has to be the next step. Okay, so by substitution, what are we substituting into? N squared. Nice, thank you. So by substitution, n squared is equal to the quantity of 2k squared. In fact, I think you guys had one of these for homework, right? With a divisibility. It almost looked like the same sort of thing. Except we're trying to show divisibility by 2. Okay? What do you guys think? Yeah, multiply it out. We'll get 4k squared. Sweet. So that equals 4k squared. Okay, by multiplication. And then factor, and how would you factor that? Like 1/2 times 8?
Not 2.
2 times 2. I'm just trying to be as smart as.
You could do it that way, it wouldn't help.
I could, but it would not help. You are absolutely right, Mr. Weber. All right, it'd be completely fruitless for me to do it that way. Okay. So yeah, we can just factor off the 2 and get 2 times 2k squared. Okay, that's just by factoring, computation, multiplication, whatever. And guys, what do we know about 2k squared? Some integer. Let's call it m. Did you say m too? Wow. That's crazy. Are you mind
minds think alike, yeah.
Bro, no, I'm not a great mind.
Not with that attitude.
Ouch. I've got spirit, yes I do. All right. So guys, that's by closure, right? And clearly what we've shown is that the contrapositive is true, okay? So, this is by closure. Okay. And what we can say is that thus, n squared is equal to 2m, and is even by definition of even. Which means that the contrapositive is true. Okay, so thus the contrapositive is true. Which means what?
The original statement is true.
The original statement must be true as well. They're logically equivalent.
So
Thus the contrapositive is true, which means the original statement must be true. Thus, the original statement must be true as well. Okay? Or we just say must be true. Easy enough, right guys? Okay? Go ahead, Brian and then Greg.
And why couldn't we have done the original?
Because unfortunately, okay, that's a good question. Okay, so let me let everybody copy that down. But if we wanted to just use a direct proof, right, we would say that, what was it, if n, we said if n is an element of I, right, n squared, no, we said if n squared is in Zi, then n is in Zi. Right, okay. Now, this means that n would have to just be any integer, right? So unfortunately, if we try to do this, we could set n squared equal to 3, right? But it's not a perfect square, okay? So unfortunately, we don't have a definition for a square root that we can utilize, okay? We just don't have that operation going on. So the only way that we know how to work with this is just the contraposition method. Does that make sense? Just because of the square root operator, right?
I was wondering, when we did the substitution step here, why did we only take the step for the n squared? Is that because it's the only one that matters?
Oh, right, because we're trying to prove that n squared was even.
Oh, right.
Because remember, when you do the contrapositive, we said if n is even, then n squared must be even as well. Okay? Does that make sense now?
So you only care about that n squared?
Oh yeah, we only care about the then. We're only trying to prove the predicate, not the antecedent. Alright, other questions, guys? Okay. I can do the other one for you guys, but what I think we want to do is, I'm just going to go ahead and work this out and post it on Blackboard for you guys. I think most people would be pretty good with doing that, okay? But it's basically just like a divisibility proof. Plus I need to get back to your assignments, so. Any questions, guys, about anything that we did with either contraposition or contradiction? Okay, so let me give you guys back your assignments. Okay, if you guys have some questions for me, I'd be happy to stick around and answer those questions for y'all.